This is the second video on the lesson for implicit differentiation. We're going to start with an example for finding the equation of a tangent line. In order to find the equation of a tangent line, we're going to need to have the formula for the equation of a line in point-slope form, which is y minus y1 equals m, or slope, times x minus x1. And we are given the points x1 and y1, and we're also going to use them to find the slope. And of course, the slope comes from finding the derivative. So we're going to take the derivative of both sides of our equation, and I get 4x cubed for the first term, and the second term is going to be a product rule where my first function is x squared and my second one is y squared. So if I do the derivative of the first, I'll get 2x times the second, which is y squared, plus the first, which is my x squared, times the derivative of the second. The derivative of y squared is 2y times dy dx, equals the derivative of y squared is 2y dy dx. So now I want to get my dy dx terms on one side of the equal sign, so I'm going to subtract 2x squared y dy dx from both sides, and that will give me 4x cubed plus 2xy squared on the left and 2y dy dx minus 2x squared y dy dx on the right. And I'm going to swap the left-hand side and the right-hand side in order to get dy dx on the left. And I'm going to factor out my dy dx's. When I do that, I get dy dx times 2y minus 2x squared y equals 4x cubed plus 2xy squared. We'll divide both sides by what's in the brackets. And as I do this, I notice that there is a 2 in common to every single term. So we'll simplify our derivative by factoring out a 2. And 2 over 2 will go to 1, leaving me with 2x cubed plus xy squared over y minus x squared y. So now to find our slope, we need to evaluate our derivative at our point square root of 2 over 2 square root of 2 over 2. So when I plug this in, I get 2 times the square root of 2 over 2 cubed plus square root of 2 over 2 times the square root of 2 over 2 squared over the square root of 2 over 2 minus square root of 2 over 2 squared times the square root of 2 over 2. Now this is really ugly, but if I do the arithmetic, all of this actually simplifies to be 3, which is our slope. So now we have a slope of 3, and we have a point x1, y1 is root 2 over 2, root 2 over 2, and we can plug that in to point-slope form. So my equation becomes y minus the square root of 2 over 2 equals 3 times x minus the square root of 2 over 2. In point-slope form, that is the equation of our tangent line. If we choose to go a step further and find the equation in slope-intercept form, I'll have to distribute my 3, which gives me 3x minus 3 times square root of 2 over 2. And then we would have to add square root of 2 over 2 to both sides, giving me y equals 3x, well, negative 3 root 2 over 2 plus root 2 over 2 is negative 2 root 2 over 2, which can be simplified. And we end up with 3x minus the square root of 2. Okay, we can also find higher order derivatives using implicit, and we're going to find the second derivative of this problem. So, I do this almost the same way we do regular differentiation, but there's going to be an extra step in the end. So, we take the derivative of both sides, and on the left I get 2x plus derivative of y squared would be 2y times the dy dx equals 0. Subtract 2x from both sides, and I get 2y dy dx equals negative 2x, and divide both sides by 2y, and we get dy dx equals, if I simplify this, negative x over y. Now I'm going to leave that negative in the numerator because we are going to have to do a second derivative using the quotient rule, and I need to assign the negative to either the numerator or the denominator to be able to use the quotient rule. So now we're going to take another derivative of negative x over y, which remember came from the function x squared plus y squared equals 25. So when I do the second derivative, we do low from the quotient rule. Low is y, d high would be negative 1 minus high, d low would be a dy dx over low squared. So if we clean this up, I get negative y plus x dy dx over y squared. And the extra step that's involved when the second derivative is implicit is that we cannot leave a dy dx in our answer. However, we know what dy dx is, so we can just substitute it in. So my second derivative becomes negative y plus x times negative x over y squared. And if we clean that up, we get negative y minus x squared over y squared. And that gives us a complex fraction. We're not allowed to leave things in terms of complex fractions. So we need to get rid of the inner fractions denominator by multiplying the numerator and the denominator by that. And when we distribute this y to the numerator, I get negative y squared, and then for the second term the y's cancel, so minus x squared all over y cubed. Now, I'm going to rearrange my numerator a bit here. I'm going to factor out a negative 1 and write it as negative times the quantity x squared plus y squared over y cubed. When I do this, I see that x squared and y squared was actually my original equation, and it is equal to 25. So my second derivative can actually be written as negative 25 over y cubed. That will not happen in every problem. That is just something that happened in this problem and was interesting to see. We're going to do one more second derivative. So for this one, we're differentiating y squared equals x cubed. I'm going to take the derivative of both sides. On the left, I'm going to get 2y dy dx, and on the right, I get 3x squared. Divide both sides by 2y, and I get my first derivative is 3x squared over 2y, which cannot be simplified. So I'm going to rewrite this so I can see what I have to do the quotient rule on. So our second derivative then is low, which is 2y, d high, which is 6x, minus high, d low would be 2 dy dx over low squared. So if we clean this up a bit, we get 12xy minus 6x squared dy dx over, let's actually square our denominator, that would be 4y squared. We're not allowed to leave a dy dx in our answer, so we're going to substitute in our first derivative, and we'll clean this up. Six times 3 is 18, and 18 over 2 is 9. And we get times x to the 4th over y over 4y squared. Again, we have that complex fraction, so we're going to multiply the numerator and the denominator by y. Distribute that to everything in the numerator, and we get 12x y squared minus, in the second term the y's cancel, that's why we do it. We get 9x to the 4th over 4y cubed. There is no factors in common to all of my terms. There is nothing that can be simplified. This is my final answer.